Hi, my name is Emily Centamore, and this semester I've been working through the Randall Research Scholars Program under Dr. Sergei Gleyzer in the Department of Physics and Astronomy. Our lab has been working on upgrading detection and analysis capabilities of the CMS Detector for the High-Luminosity Large Hadron Collider. In this presentation, I'm going to give you some motivation and background for the work we've been doing, the methods that we've used, and the progress that we've been able to make this semester. We'll start with some motivation and some background. The Large Hadron Collider is a 27-kilometer circular underground tunnel that uses magnetic acceleration to create high-energy collisions at 4 major detection sites around its circumference. Our lab focuses on the CMS detection site, or the compact Muon solenoid. The CMS detector is a cylindrical detector with layers of detection technology. The outermost layer contains muon chambers, followed by a large solenoid magnet, 2 calorimeters, and silicon trackers in the very middle. The detector collects information from collisions in the center as particles explode outwards to reconstruct an image of the collision that looks something like this. You notice in particular that there's the highest particle traffic on the flat ends of the detector, known as end caps. But not all of the images look like this. Some of them are a little bit more complicated with more particle paths, like this. This is called high pileup. But still notice there's the highest traffic on the end caps of the calorimeter. Collisions like this are going to become increasingly common with new upgrades to LHC, which will be known as the HL-LHC, or the High-Luminosity Large Hadron Collider. This just means that there's going to be a higher rate of particle collisions so that we can collect data on more rare particles more quickly. However, as part of this, our detection hardware is also going to have to be able to withstand higher levels of energy. Our upgrade in particular focuses on the end caps of the calorimeter, known as the HG-cal, or the high granularity calorimeter. One of the main goals of this upgrade is to increase the radiation tolerance of our end caps. However, we're also going to increase the resolution of our data, hence the name high granularity. We are going to have a hexagonal tessellation of hexaboards that will be spaced closely together so that we can collect information from those high density particle collisions with more precision. Our job at UA specifically is to perform visual inspection on the hexaboards. Visual inspection happens between the production and assembly stages to make sure that there are no defects on the board when it first goes into the detector. This, as you can see by the small parts on the hexaboard, is kind of time-consuming to do by hand, so our job has been to make a method that's faster using computers. So we're going to look a little bit at that method now. Our first step is to capture images of the hexaboard. We do this using a scanner that was developed in the lab. It is composed of a webcam mounted onto a 3D printer setup so that we can take small grid-like images of the hexaboard in segments. The use of the webcam allows us to have high resolution of images and also focus depth, and the small segmented images reduce our warping around the edges of the image. We can then put all of the image segments together to form a complete picture of the hexaboard. We are inspecting the images using 2 different methods, pixel-wise comparison and an autoencoder. The combination of these methods increases our accuracy in catching faults on the hexaboard. So on the left-hand picture, you can see a close-up of a gold connector piece on a hexaboard, and those can sometimes have glue leakages, and pixel-wise comparison is good at catching those kinds of errors. Whereas on the right, you see a close-up of capacitors on the hexaboard, specifically a missing R19 capacitor, and the autoencoder is better at catching missing components like that. So we'll start with an explanation of pixel-wise comparison. In a pixel-wise comparison, we do a direct comparison between our input image and an image of a known good hexaboard. We convert the images to grayscale and assign them index numbers according to the gradient that you can see across the top of the slide. We can then compare the pixels corresponding between each of the hexaboards and find their differences between their index numbers. We can then compare the difference of each pixel to a threshold that we have set. And if the difference is higher than the threshold, then we flag the segment as having an error. Our other method is using the autoencoder. This is a little bit more complicated, but we'll start at the base of it. The root of an autoencoder is a neural network. A neural network is characterized by its use of a cost function to minimize loss. A neural network works by taking in an input and returning outputs as if it were answering a multiple choice question, and it assigns probabilities to each of its options according to how likely it thinks each answer is to be correct. The neural network reaches its decision using a set of probabilities known as weights and biases, whose value can vary from 0 to 1. However, not all values of a weight or bias have an equal efficiency. Some values can maximize efficiency or minimize loss. The continuous representation of this relationship between loss and weight or value bias is known as a cost function. The optimization of weights and biases using the cost function is known as training. The goal of training is to teach the network to return the correct output with as much certainty as possible. In an autoencoder, the neural network is just the machine learning base behind its larger ability, which is convolutions. A convolution is performed using an array of numbers known as a kernel, which we overlay on the grayscale image. Each pixel associated with the square of a kernel is the input for the kernel, which the kernel then averages and returns an average colored pixel as the output. In a convolution, the kernel slides across the image, producing an averaged output for each set of its inputs. The result is a simplified image of the original that frequently has a lower dimension than the original image because each of the outputs took in more than one input. The goal of kernel optimization is to make sure that we can use the convolution process for feature identification. In an autoencoder specifically, we use convolutions and deconvolutions for image identification. A deconvolution just means we re-expand the simplified image using something called a transverse kernel. The way we train our autoencoder is by giving it only perfect inputs so that it can only give us back perfect outputs. We can use this to our advantage because we know that even if we give the trained autoencoder an imperfect input, it's still going to give us a perfect output because of its training. So we can use our trained autoencoder to inspect our hexaboards by giving it hexaboards that we don't know if they're perfect or not. And if the output of that inspection process is different from the input, we know that there's a flaw in our input, and we can compare our images to find the flaw. Finally, we'll look at some progress that we've been able to make this semester. This semester, I started with working with some people to look at the already existing code for our autoencoder. So the first step was to create some flowcharts to allow us to visualize what was going on with the code and spot any repetitions or redundancies and ways that we could make the process more efficient. We then used the flowcharts to do just that. We were able to organize our code better so that we're going to be able to communicate it better in the future and make our process as efficient as possible, which will be important once we start getting in the high volumes of hexaboards that will be coming. Our next job was to calibrate our scanner, so making sure that our hexaboards were the correct distance from the camera and to make sure that our lighting was the best so that our images would be as advantageous as possible. You can see in some of these images some different lighting options. So in the top left, some daylight, which is okay but independable. The top right, a lot of glare. In the bottom left, blue lighting, which doesn't give us a lot of contrast. And in the bottom right, some greenish yellow, which is our best option, but this is something we're still working on. Our last step will be to format our results to make our data as efficient to give out as possible and analyze our hexaboards the best we can. So we're going to experience some increase in production over the next couple months, and our work is to help ensure that good hardware is used in the final detector. Our hope is to stay on schedule so that the LHC can reach completion by 2030 and we can keep running particle experiments and collect data on how the world works. These are my references. Do you have any questions?
Two short questions. So first, Can you clarify like how many hexaboards are you processing? And then another question is on slide 12, you're talking about accuracy. Can you give us, you have a feeling yet for some numbers or how, where's the accuracy levels at?
Okay, so for your first question, the hexaboards are several centimeters across and our detector is about 15 meters across. So that's going to mean that we're going to have to go through several thousands of hexaboards in the span of a couple months. So that's where the importance of efficiency of our project comes in. You were talking about slide 12.
Slide 12, you just referred to accuracy. I just wondered if you have any accuracy or intuition about what that would be for each of these.
So the reason we combine the methods is to increase the accuracy in the sense that we're not missing things. So the autoencoder may not catch issues with the gold components, and the pixel-wise comparison might not be as good as at catching issues with missing components. Is that what you mean?
Are there some you're still missing, or are you hitting everything that's wrong? Are you finding it, or are you missing some still?
So right now, we don't have enough hexaboards that we're actually running those tests yet. So this is all theoretical until we start getting shipments in.
So I was curious about like what the outputs of your models actually look like. Is it just like a perfect, imperfect like classification, or is it actually like if it finds an issue, it feeds back out what location on the hexaboard is like incorrectly manufactured? Like what does the outputs look like?
Yes, so with our inspection system, the ultimate output is going to be the list of flag segments. And the goal is ultimately to have a user interface that's going to show you, like, kind of in a grid, give you some coordinates of where exactly that is.
What is the actual job that the hexaboards are doing in the detector?
So the hexaboards are actually one layer in kind of a multi-layer module that gets put together in that tessellation. So a different layer in that module is detecting the particles as they explode, sort of. And then the hexaboard's job is to convert the data that those trackers collect and convert it into like computerizable information, so like electrical signals that we can interpret.